Well, good evening, AP Physics. We're going to be talking about thermodynamics today. Heat engines. We're going to get our motors running and head out on the highway. Looking for. All right. Let's start out today talking second law of thermodynamics. So we learned equation, a statement equation of energy. But the second law of thermodynamics seems pretty straightforward. It says heat only flows spontaneous from a hot object to a. Now this kind of seems like common sense. Heat flows from hot objects to cold objects. But it is important enough we've called it the second law. See it stated that we've stated it will only flow from a hot object to a cold object spontaneously. You also see it stated the other way, where heat will not flow spontaneously from a cold object to a hot object. Now, what do we mean spontaneously? Well, you know, your refrigerator is a heat pump, and it takes extra work and pumps hot air on the inside of the fridge out, making the inside cold. So if you do enough work, you can make a heat pump and add extra energy to move heat from cold places to hot places, but it won't happen spontaneously. Okay, and since we know about this flow of heat from hot objects to cold objects, we can use that flow of energy to make a heat engine. And a heat engine is any device that changes thermal energy into mechanical work. All right, mechanical work. So, your car engine is a heat engine. A steam turbine that makes electricity is a heat engine. A steam locomotive is a heat engine. And here's how all heat engines work. You have a hot reservoir and a cold reservoir. And in an ideal heat engine, this hot reservoir is at some hot temperature T sub H, or high temperature. And the cold reservoir is at a low temperature, T sub L. Now, heat spontaneously flows from the hot to the cold, but some of the heat we turn into work. All right? So, of course, we can't destroy or create energy. So all the heat energy that flows out has to equal the heat flowing into the cold reservoir plus the work. So Q sub H has to equal W plus Q sub L here in order for energy not to be energy to be conserved. We can't create or destroy energy. So the efficiency of this system is defined by this. The efficiency of a heat engine you can think of as being the percentage of the heat that gets turned into the work. All right. Right now, the way I have this drawn, it looks like the efficiency would be approximately 50%. So about half of this heat that's flowing gets turned into work. All right. So since Q sub H is equal to W plus Q sub L, we could also rearrange this into many permutations using these two equations. Sometimes you'll see this where this is written as just T sub H minus T sub L over T sub H, where instead of talking about the heat flow, you're talking about the temperatures. Well, guess what? The temperatures are proportional to the amount of heat flowing, so those are really equivalent equations. Okay, keeping this diagram in mind, let's tackle problem 17 from your homework tonight. Problem 17 says I have a heat engine, and the heat engine does 3,200 joules worth of work each cycle. Okay, and it also says that each cycle that this engine operates in, engines tend to operate in cycles, 8,200 joules worth of heat flow from the hot reservoir to the cold reservoir. What is the efficiency of the engine? Okay, so the amount of heat flowing out here then must be equal to W plus Q sub L, or 3,200 plus 8,200. So Q sub H is equal to 11,400 joules. Okay. So 11,400 joules of heat flow out of the hot reservoir each cycle. Of that, 3,200 joules gets turned into work. The other 8,200 joules goes to the cold reservoir. So if we to calculate the efficiency here, that would be equal to 3,200 divided by 11,400, which turns out to be 0.28, or as we often describe efficiencies as a percent. So if you divide this out, you get 0.28 or 28%. All right, nice work, physics students. Your inspiring story for today is, I know many of you grew up with Pluto being a planet, and while Pluto is no longer a planet, it's a dwarf planet. Have no fear. The New Horizons satellite was launched in 2006, and we actually know very little about Pluto and Charon, which are now classified as dwarf planets, but in just 2 short years, we will know a ton more about them. So anyway, I thought that was a cool story about the perils of Pluto, and that was in this most recent episode of Discover Magazine. So I'll have that in class if you want to check that out. All right, nice work, AP Physics students. We'll see you tomorrow.